So I continue to the talk about yesterday that how heat losses, how that the Lewis number, how that the heat addition and the chemistry may potentially affect ignition and flame speed. And then that in a strain environment, in your flow stage, we depend on the mixture Lewis number, your flammability limit could be lower than the conventional flammability you think. It's because that in a competition between heat loss and then Lewis number effect. I hope that conveyed that message to you yesterday. And today we try to answer another question that a few years ago, and is that a aircraft a relight problem? As you know that when the aircraft, military aircraft, when you fly at a high altitude, and then you try to relight it, that when for chasing, for escaping, for any kind of purposes. But sometimes that relight failure, that you cannot ignite at this environment. Afterburner is not on by the spark plug. And still, this problem is still working on it. So that is the only thing that the industry try to working on it is that try to increase more power. So or that it is a flame speed problem, that the flame speed is too low and they cannot ignite, cannot maintain it. So that time I was thinking about this. If you're going for the altitude, that the pressure will decrease, right? For anybody took that the combustion lecture will know that the flame speed for jet fuels increase with the decrease of pressure, correct? Because the diffusivity is lower at high pressure because the reaction order is what? Yes, pressure order is negative for alkanes. So flame speed basically increase as you go to altitude. So therefore that then you can see that the flame speed and the flow speed is basically increasing, and with that the flying speed, but that as you fly speed faster, that means you fly higher, and that the flame speed actually is increasing. So the relight failure at high altitude, at low pressure, cannot be blamed because that the flame speed is lower, and the flame cannot be stabilized there. That's wrong. There must be something else that governing that you cannot ignite the mixture, right? So that was the question. I think that probably 10 years ago I was thinking about that problem. And then, so everything that they said, if anybody do spherical bomb experiment in this class, if you do, and you do that, you will see that every time we try to ignite it, the ignition becomes difficult when you get into a low pressure, right? It's getting easier when you go to high pressure, right? So therefore, again, it's not a flame speed problem, right? It is something else. So you conventionally basically say, what is governing that ignition process and what is the minimum ignition energy? And that has been textbook, many combustion textbook. And they basically say that as long as you can create a flames with a thickness that is equivalent to the thickness of flame thickness, and at the temperature of adiabatic temperature of that mixture, ignition is done. Okay, you can initiate the ignition. So the question that what is that the transport effect here? Because plasma is going to break down the fuel to small ones. We have to understand what is Lewis number. Everybody knows what is Lewis number. I don't want to elaborate more. If you look in the textbook of the von Lewis and von Elbel from 1960s, Paroni and Overglassman's book, you can see the minimum ignition energy is defined by a small volume. That volume is a sphere with a thickness of delta, flame thickness. If you can create a small volume with a radius of flame thickness and raise that temperature to an adiabatic flame temperature and multiply by the capacity, specific heat and the density, this is the minimum energy you need to be. Okay, so if this is true, and you can analyze flame thickness is inverse proportional to the flame speed, and then flame speed is proportional to the Lewis number, you can see that ignition energy is decreasing when you increase the Lewis number. That is against the experiment. When you ignite hydrogen, is in a spherical bomb, it's easy to ignite. When you ignite jet fuel, the larger the molecule you go, it becomes more difficult to ignite. So this one is not contradicting to the experimental observation. Okay? So the question that what really governing the minimum ignition energy? So that is 2005. I was sitting with my former student, Professor Chen Zheng, and I said, what is that thing going? So there's another one, Theodorovich. Theodorovich is a famous theoretician. And if you see something he said is wrong, then you are a big deal. And then he said that ignition energy is not governed by flame thickness. Ignition energy is governed by a flame ball. How many people heard about the name of flame ball? Okay, you don't know what is a flame ball. You know what is flame ball. Or flame ball. If you have a uniform mixture, quiescent mixture, and then if you ignite it, and the flame may propagate outside. It becomes a propagating flame, right? But for some mixtures, let's say hydrogen, very lean hydrogen, you ignite it, the flame, if the mixture is very lean, the flame propagates outside and then shrink back and just like a ping pong ball sitting there forever. That flame has no speed, 0 speed, but has a size. That size we call flame ball size, okay? Flame ball exists for all mixtures, no matter what is the Lewis number, theoretically. That's what Theodorovich in 1980s found that. He has theory and showed that flame ball exists for it. But no flame ball is stable in his theory. He said, analytically, I have a solution of flame ball for all mixtures with all different Lewis numbers. But if you perturb that solution a little bit, and then all the solution diverges, either the flame ball collapses to the center, disappear, or propagate outside to become a planar flame. In his book, he basically concludes that flame ball is not observable. Okay, until 1990s, the one guy at Princeton was the assistant professor at the time, was Professor Paroni from USC. He did this a microgravity experiment. He saw some ball there, stationary and stable. He said, oh, this is a flame ball. Why would that Theodorovich did not say that this could be stable? And then he couldn't explain it. And then you find that another person came in, that is a brilliant mathematician, that John Buckmaster. Do you know, anybody know his name? Well, you should know more combustion theory. John Buckmaster came in. He introduced a radiation heat loss in energy term, because radiation is governing that the flame burning limit. He put in one term, radiation, and then he found that the flame ball can be stable even with perturbation if the Lewis number is less than 1. And then people start to measure flame ball until NASA running out of money, and in 2000, 10 years later. Okay, so I was really attracted by these beautiful things. When I saw Paroni's flame ball, and I saw that the experimental we did is that I showed you yesterday, that the C curve, I could not examine it until I introduced radiation. I can predict the same thing as I did. So Paroni and we did the different thing. He did flame ball, and I did the straight flame. In 2005, I want to unify the two things together. Flame ball, you don't have any stretch because you don't have speed. And then the C curve I showed you yesterday, it has a stretch. And then can we develop a theory that link them together? You can show you both flame ball and the straight flame. So that's what I tried to do in 2005. So this is the opportunity, is that you have two groups of people, both of them are really famous, and in that field, they have a contradictory result. One of them that they say ignition energy is the inverse of Lewis number, which is not true, and for experiments. The other basically say it's proportional, looks like it, but not really it. Okay, so must be one of them is wrong, or none of them is right. Okay, so that is an opportunity for research, and that is what is the impact. It can impact the advance of science. So now that what we did, that time is a very simple asymptotics, and you know Professor Matalon, he's an expert in that area. I learned a little bit of scale when I was young. And so you can see that the only thing that traditional asymptotic theory, they only made two assumptions. One, quasi-steady state. Flame basically is quasi-steady state. Two, the radius of the curvature is very large compared to the flame thickness. But this assumption is not accurate when you consider a ignition, spark ignition. Because when you spark it, the flame kernel is really, really small, right? Particularly at low pressure, that radius is probably comparable to your flame thickness at low pressure. So that assumption falls apart. So we got to remove that assumption. So we try to solve this thing accurately without any assumption that R is much larger than the film thickness. You can directly solve this equation by directly integrating it. Unfortunately, I had a great student. When you are a professor, you had a smart student, and they can do it. And then this is that way Jen Chang did it. He found that a solution of this flame speed as it is propagating outside, the speed of this, which is U, is governed by the energy you put it in the center. It's governed by that the Lewis number of the mixture, and it is a function of the radius, and then it is a function of the chemistry, Zerdovich number. So this theory is deriving the flame dynamics with no assumption about Lewis number is small or unity, or the curvature is larger a bit. You should be able to predict everything you should see. And you can introduce a heat loss here, H, to representing that radiation heat loss. That gives you a complete diagram of flame speed as a function of radius and heat loss, right? And as a spark energy. I talked a little bit yesterday, but I'll try to give you the. So now this is at the result, for example. I talked to you yesterday that as a function, you see that the flame speed normalized by the adiabatic flame speed should be 1 when the radius is infinity. And when the flame speed goes to 0 is here. So this is that the flame ball size. When the flame speed is 0, it is a flame ball. But when the flame speed is not 0, and then this something between is the flame dynamics. So this is the Lewis number is equal to 1 for adiabatic case. You're adding a different ignition energy, and then the smaller they go here, and the larger they can go here and then go ignition. Ignition failure, ignition success, success depends how big that your energy put it in. So the bigger the energy does create a successful initiation. But really the thing that is the critical radius here, you have to drive the flame. Any flames beyond that, larger than that, it will go by itself, right? So what if the Lewis number is larger than 1? And you can see that if the Lewis number is larger than 1, you need a much bigger energy to ignite it in order to drive it. So two conclusions that there is a critical radius that governing that the flame success. This critical radius is neither that the flame thickness nor that the flame ball radius. This is the flame ball radius, remember, is by this one. So this is the critical radius, this is flame ball radius. So this is that the first time we show that the critical radius make a big deal in terms of ignition theory. And then if you look at that for adiabatic flames, you can see that for all mixture Lewis numbers, from Lewis number 0.5 to 2, and then from, let's say, something like hydrogen, something like a propane, every adiabatic flame, they have a flame ball with velocity 0. This flame ball size is the Zerdovich flame ball size. So you can see that this theory basically linked that the flame speed at far field and the flame speed with stretch rate and flame speed of flame radius of flame ball. So all of them, they link together in one diagram. So this, that is the flame ball size. So this critical radius governing the ignition energy. So this is the theory. And then what if you do a numerical simulation? Today everybody can do a DNS, right? If I do a DNS, can I predict that this ignition energy, successful ignition energy, is indeed proportional to the cubic of this critical radius? If it is, this critical radius governing the minimum ignition energy, right? So here that a diagram, you can see that if you don't have a spark plug, and this is that the flame diagram. Any flames below this, it cannot sustainable. If you add a little bit of ignition energy, you can see this is the ignition kernel and the field, and then the flammable region extended. Add more energy, you can see that the ignition kernel here, and more energy, and eventually this is at the critical flame radius. And there, this is at the energy you do, number 5, this is at the critical energy, you put it there. Beyond that energy, the flame kernel will be driving bigger than the critical radius, and ignition will be successful, anything will go. If you plot this critical radius, you take a cubic of it, and then you plot that how much energy you have to dump in a numerical simulation. And you would expect a linear dependence if the theory is correct, right? So indeed, you can see that all this kind of minimum ignition energy for mixture is proportional, linearly proportional to the critical radius of ball. And no matter what is your Lewis number, okay, from small to large, you can ignite it. Second thing observation from this figure is that as your Lewis number increase from smaller to higher, and your required ignition energy getting bigger and critical radius getting bigger. That means that if you want to ignite the larger alkanes or larger aromatics, you need a bigger ignition radius and you need more ignition energy to happen. Okay? That's the takeaway. Second message. The third message is this. Third message is that by changing that a zero-deviation number, which is that activation energy, with a different activation energy, and then by reducing the activation energy, and your critical energy actually reduce. That means that if you're using plasma to change the reactivity, to reduce the activation energy, you could potentially do 3 things together. One, that drive the ignition kernel larger than the critical radius, directly ignited. Second, that break down the larger alkanes to small ones and reduce that Lewis number so that you reduce that ignition energy. Third, create a new reaction pathway that reduces the activation energy so that you can help you to ignite it better. Okay? So this is a simple theory, but you have a lot of takeaways when you're using it. That's why I always said that when I was graduating, I really inspired by this kind of things. And they're very simple things. And probably nobody care about it, but they tell you a lot of things. And if you try to do trial and error experiment, it takes many days or years to finally figure it out. So what is the critical radius for jet fuel? So a few years ago, I was funded by Air Force to find out that what about the JP8 and what about that the shell and synthetic parasanic kerosene and all this kind of different fuel. What is the critical radius? If you measure it in the laboratory at 1 atmosphere pressure, you can see at 450 Kelvin, depending on the fuel, the critical radius is about 1.5 centimeters, between 1 to 2.5 centimeters large. So in a gas turbine relied problem, and your pressure of that in the relied region is around how much? How much? Half atmosphere, around half atmosphere, right? It's below the 1 atmosphere. So your experimental data must be higher than 2 centimeters radius in terms of a critical radius. So you have to generate a spark, a plasma, which is bigger than 2 centimeters in order to ignite that mixture, correct? But no one thought about that way. Everybody thought about adding more energy is going to do everything. But adding more energy is only generated very high temperature, which you don't need to ignite anything, and then eventually burn down your ignition spark igniter, right? So this is that to tell you that what is the strategy you need to do, particularly improve that the igniter for afterburner. I was in GE about a month ago. I told them that this is that the idea you have to adopt in order to prove the ignition igniter for afterburner. Right now, they only can optimize the energy. So that's another thing. Energy is not the one thing. right, governing the process. So this is at a spherical bomb. For example, many of you did the experiment, and you can generate a chamber and with a housing, and you put a whatever fuel, liquid fuel into it, and you spark it. You can measure that the ignition energy. You can measure the critical radius. And this is what you see. You see the flame spark and then generate. You can see that the trajectory of flame speed. Here is the ignition corner, and the flame speed decreases, and propagate by itself, and eventually get into the adiabatic flame speed. See what I'm saying? The theory, even though it's simple, one step, constant property, quasi-steady, they tell you almost the same thing as you saw, and in the experiment, even though that this is probably end decane, it's a very complicated field, right? So then you can see that this is how the flame radius change. So if you recall that the theory predicted, this is exactly the same thing as the theory predicted like that, you know. So what we really to learn from this one, that means that the plasma assisted ignition, particularly for lean mixture in the engine in the future, and it's not that the first priority to increase the energy. It is the first priority to how do we create the larger ignition corner and using a non-equilibrium plasma, okay? Instead of raising the inner temperature using a small spark, okay? That is the key. That is the new things, and the academia and the industry need to figure out how to do that. I don't want to say more about that. So the next question, when you talk to GE, and he will say, okay, what you're talking about is a quiescent mixture, right? What if I have a flow? And if does your theory or does your experiment and still valid? So I had fortunately I had a graduate student, Tim Umbrello, and working in Air Force, and he conducted an experiment that he has a flow in the channel. He has a spark here. He can vary the flow rate in the channel, can be laminar or turbulence, but he can adjust the gap with the same energy, right? If the theory is correct, you would imagine that with the same energy, the small gap will be difficult to ignite, and the larger gap will be easy to ignite until you cannot form a spark, correct? Okay, here's the experiment. So I'll show you the result. So you can spark it, and then you can generate that the ignition kernel. So that ignition kernel may develop into a flame and may not, depend on that the frequency. So where is it? Okay, here it is. So then you can see that the flame can be successful here, may not be successful here, eventually disappear. So so you can jot that you can plot a diagram the ignition probability at which how many percentage ignition will be successful and in that condition. Here is the equivalence ratio, okay? And here is that the distance of that spark plug, the distance, small to larger, okay? So you can see clearly that if you have something like a very small gap, like this one, extremely at 0.5 millimeters, and you put the energy there, you don't get any ignition, right? As you increase the gap size, you start to see, okay, at this one I can ignite it. As you increase more, at this one I can ignite it, and more and more. As you increase that, the more the gap of the size, and you become more successful in ignition, right? So this again, once again, prove that the criteria of critical radius and then theoretical work really work. That give advice. This paper is published 2017. You see that? So this means that give a direct a guidance how to optimize an igniter to ignite a very lean mixture. So what about that? We do it and you can say with a different kind of a non-equilibrium plasma. Here, that what he tried, and Tim Rambello, what he tried at Air Force is that using that a nanosecond plasma, and with a very high frequency, that is a kilohertz here, with a lower frequency. So what he says that the ignition probability that using a non-equilibrium plasma with a high frequency you can successfully ignite the mixture and with high probability. And or you dump all energy into a single, a spark, generate a big spark with a lot of energy, and something between that you don't generate a good ignition. But this experiment is done by a methane. Methane is a Lewis number close to 1, right? Slightly below 1. But I communicated with him, a good experiment to do this experiment using jet fuel, because the Lewis number is very large and is very relevant. And he probably will have a telecom with me and later this week to arrange an experiment doing a jet fuel. So that will be more and supporting evidence to show that even in a flowing environment, even in a turbulence environment, that the size of discharge really matters beyond, sometimes it matters beyond the energy you put it there, okay? So this is what I try to do. You can take this message. What is this guy? So this is that another extension. We're talking about that the scramjet, and people develop a supersonic aircraft, and you want to ignite the mixture, particularly when the Mach number is lower. When the Mach number is 3 to 4 to 5, it's very difficult because the temperature you come in is very low. So how do I ignite it? So this is that the experiment by Tim Umbrello at the Air Force R. You can see that ignition happened and in somewhere and the flame spread in the cavity. Is this ignition? I think it's yes. Is this just ignition? I think it probably is no. It is a combined mode between ignition and flame propagation, because that the incoming flow temperature here is quite high, right? So there is a combined mode of ignition and then flame propagation. How fast is that flame speed? When you measure flame speed in the laboratory, how many people measure flame speed in the laboratory here? Okay, we got 2. So what temperature you measure the flame speed? Room temperature. See, this is the problem of all this kind of experimental data in the laboratory. So people measure a flame speed at room temperature. Flame speed at room temperature is great to validate chemical kinetic mechanism, but it has no relevance directly with the engine application. All engine application that the temperature is higher. At higher, what changes the physics? Is because that when the temperature is higher, the autoignition time is almost comparable to that the time of a flame propagation time. So then, is the flame speed is not that the flame speed at the low temperature anymore. It's governed by solely by diffusion reaction. It's governed by autoignition and flame. Remember, autoignition time is proportional exponentially to inverse exponentially to the temperature. Flame speed is proportional to square root of that exponential term. So when they couple together, they have a different job. The valuable data in the future, you should be that the measuring the flame speed at higher ignition than current number, reactive flow. So I try to summarize this. And this is that, I read past this one, you don't confuse you much. He prepared a lot of things. So the summary about what he says, that the synergy between the pulses and then high frequency and change the way of ignition. In other words, that the design of ignition plug of plasma really changed that the approach of reactive flow. The time scale of energy deposition is critical and can couple the thermal and kinetic and flow. So there is some kind of optimum conditions, and then there is a connection to the realistic environment. So that what is his conclusion? So try to make a complicated things and in an engine, and try to make it simple so that you can using a very simple model to present an idea. Using the idea, try to explain that it's complicated things and build some bridge between them. That is the beauty of research. That's always what I do. If I can do something simple, I never want to do something complicated, because the more complicated you go, and you're difficult to explain, right? So when I came to Princeton, Professor Harvey Lam, how many people know Harvey Lam? No one. He's the one developed this computational singular perturbation method for model reduction. And he basically says that when you do a research problem, first let's look at the problem, whether the problem is dirty or not dirty. What do you mean by dirty or not dirty? Dirty means that your boundary condition and everything is not well defined. And you don't know how to repeat it, and you don't know how to set the problem. The simpler that your problem is defined, the more meaningful and then easy to explain. Okay, that's something beyond this my talk. Try to share with you. In summary, that in combustion, the most important things are the S curve, ignition and extinction. And then this limit is governed by ignition, by flame speed in a different way. So plasma can control ignition more effectively than you change the flame speed, particularly at the low temperature. And then the flammable limit is governed by two limits. One is the lean, one is the rich. Because the flammable limit occur at the critical point where the competition between heat release rate through the chain branching reaction and the heat loss are competing. At that time, plasma can play a role to extend that the Limber limit to rich limit. So that's what the plasma can do, as a burning leaner and richer, particularly when you have a cool flames. Plasma can make a much more profound effect to change your burning limit. And third, and then the ignition problem is the flame ignition problem in engines is not governed by ignition delay time. It's neither governed by the flame speed. Rather, is governed by a dynamic process from ignition kernel development to the planar flame, which is governed by the critical radius, and a plasma can play a dramatic role to generate a spark which is bigger than the critical radius, so that all mixtures in a flammable region can be ignited with no uncertainty, right? So that is something I think that the IC engine communities and the gas turbine community need to think. How do we do that to design it? If we can do that, you can form a company and do yourself. You probably can be an entrepreneurship. And okay, so that's what I'm thinking too. I mean, try to think about that too. But I'm more like a theoretical than a entrepreneurship. So summary that plasma has a both kinetic and thermal effect and ignition enhancement. And plasma has a minor kinetic effect on flame propagation speed because that the chemistry is not fast enough compared to the flame chemistry. And the main effect at high temperature and its extinction limit is mostly by thermal effect. Plasma may have a strong kinetic effect on cool flames and the propagation and the limit because that the plasma chain branching rate is much faster than the cool flame reaction kinetics. Plasma can cause fuel fragmentation and reduce the loose number, and thus enhance that flame speed and wear loose number effect and the Limber limit. The minimum ignition energy is governed by the critical radius, and plasma can play a big role to do that. Okay, so this is that the third lecture I try to convey to you in terms of the basic theory about the ignition and the flames and ignition energy, so that you have a good understanding of it and then design a new technique based on these fundamentals, right? You have to have. So the next thing I try to talk. Yes. Is break time now? So okay, we still have 20 minutes, right? Okay.
The flame ball, you said it has zero velocity.
Yes.
Right? So where does the products go if it's a spherical flame?
So this is a very interesting question, and the question that flame ball has zero velocity. Where does that the reactants come from, and where does that the product? Because that if you write down the governing equation in a spherical geometry, right? You have a diffusion term which is the inverse of r squared, and brackets r squared dt dr, correct? So because that the inverse r squared, if the r is small and the diffusion is very fast, so the product can diffuse out, and then the reactant can diffuse into it. So the flame ball only exists in spherical geometry because the r squared effect. In cylindrical geometry, you never can observe a flame cylinder. You can't, because the inverse of r is not. In planar flame, forget about it. There's no way you can diffuse fast enough. Okay, that answer your question? Okay, good. So in the next lecture, we're talking about before we get the more interesting part of chemistry effect, we talk about the Ionic wind effect. Because in the so a plasma has a thermal effect, kinetic effect, and have a transport effect, and then you have Ionic wind effect. So Ionic wind effect is very fascinating because they're causing a dynamic change about flame shape, attract enormous attention in combustion research from early time, right? When I come to Princeton, I also thought about doing this research. But I thought that this problem is too simple to do it because just Ionic wind is not much chemistry, it's not complicated enough, right? But still, a lot of people want to do this kind of research because of the beauty of the problem, because of the dynamic interest of the flame in response. So Ionic wind is generated by the ions in the flame. All flames are a weakly ionized plasma. For example, if you have a methane flame, the CH plus O reactions will generate an ion and an electron. These ions collide with water to form this kind of H3O plus. This H3O plus is one of the main positive ions in the flame. Of course, there are many others, CH, C3, H3, A plus, there are many others, but this is a major. So it's a weakly ionized plasma, I would say, because the electron number density is 10 to the 12. That is 0.1, less than 0.1 ppm, very low electron number density. So what if you put an electric field into this flame? That means, of course, electric field, then the positive ions will move to the cathode, and then electrons will move to the anode, right? So during this process, the charge will start to separate because the electric field, and the ions will start to collide with neutral molecules and bring the neutral molecules to move together with them, right? If you have a lot of people and somebody try to rush it out and collide you, and it will collide with that, generate a flow. So this Ionic wind, during the collision between the ions and then the neutral molecules, can be reached to the magnitude of 10 meters per second. How do you make a good use of 10 meters per second? In flames, it's a big deal because your flame speed is normally, except hydrogen, your flame speed is normally half a meter per second, right? So therefore, the Ionic wind has a potential way to swing your flames because it's much bigger than your flame speed, right? And in boundary layer, airplanes or boundary layer, your boundary layer's velocity is what? 0, isn't it? The skin friction, all of the government in the boundary layer, flow separation, your flow velocity near the boundary layer, at the sublayer, nominal sublayer, is almost 0. If we can generate 10 meters per second Ionic wind in the boundary layer, you can dramatically control the flow separation, isn't it? So therefore, due to the different magnitude between the Ionic wind speed and flame speed, the Ionic wind speed and the boundary layer velocity, so this Ionic wind has been potentially researched to control flames, to control boundary layer of flow separation of airplane. Right? Air Force has long-term funding this kind of flow control using plasma. It's basically using this Ionic wind to do that. But the fluid mechanics people are very interested in this because they generate a new perturbation and generate inverse of boundary layer velocity. Is very interesting. Right? And now I'm not talking about flow control, and we're trying to talk about flames. So if you're using a DC like that, if you're using AC, you can imagine that the ions go this direction, come back to this direction, depending on the phase of the AC, right? So if that frequency is large enough, and these ions cannot catch it up, and what does it do? So that basically there's no Ionic wind anymore. So the Ionic wind only exists in a certain frequency and DC, right? So this is at the time scales. So combustion time scale, mostly about a millisecond order of magnitude. And then you have a microwave, for example, that is much shorter than this guy. And then you have a electron neutral collision, that time scale is larger than electron neutral collision, 10 to minus 9, 10 to minus 10 electron collision, right? So this one is larger than that. For AC, and you can combustion time is pretty much comparable to your oscillating frequency if you are kilohertz, right? And if you have DC, of course, that the combustion time is shorter than the time scale here, and this is a time frame. So when you're looking about the control, you have to think about a few time scales, what time scale you are working on, right? This is that about the flame speed. So the next thing we try to talk, if you talk about ionic wind, you say that I have anode and I have a cathode. So you have the ions flowing, positive ion flowing to this direction, and electrons go to that direction. So when the ions collide with the neutral molecule, and they exchange the momentum. So that neutral molecules gain the speed. The more you collide, and more then. So that's how the ionic wind is generated, correct? And then if you add a boundary layer, the turbulence boundary layer, enamel boundary layer, if you put a discharge anode and a cathode somewhere here, and you generate a discharge between them. Once you generate discharge, the ionic wind will follow that direction at the boundary. You can potentially control the boundary separation, right? So this is the idea. So in a flames, that when you have ion, they collide with a neutral molecule, they have velocity difference, and they change the momenta between each other. And when you change a momenta, that means that you are changing, you have a force acting on the neutral molecule, right? You just have acceleration. When you have ion flowing in the direction, you just have some kind of acceleration. So this is that Bunsen from a flame, and if you put an electrical field, you can see the flame become like that. And for a long time, and Air Force Base, particularly Bish Ganguly and his group, basically think that this is because that the electrical field causing some kind of preferential diffusion that causes instability. I think that is negligible. Most of the effect is due to that. This is a kind of instability, right? Do you know Rayleigh-Taylor instability? It's caused by what? By the gravity, right? By the acceleration, right? And when you have ionic wind, you are acting a force on that process. You are acting a force. That force is similar to the Rayleigh-Taylor instability, okay? Particularly when you have a density gradient, they can accelerate the instability and then generate this kind of a surface, okay? And then you have a energy transfer because that the electrons and the gas, they also collide. The electron has gained energy easily because the mobility is higher. So that energy is transferred to the neutral molecules and overheating. So you have two effects affect the flame. One is the momentum transfer forming the ionic wind. Second is that the energy transfer between thermal energy. Okay? I'm watching the time. Don't worry. So this is that the ionic wind earlier that Calcutt, and he was a professor at Princeton, I said it before, that you put that the Bunsen flame, you can put the 15 kilovolt, you can see the flame is bending towards the electrode, depending on the positive ion or negative ion. Mostly it's negative ion. So here that the Weinberg also did a similar experiment, and this is that the Professor Charles shared this slide with me, and said that this is a flame. So if you have two electrodes, positive and negative, if that the ion mobility and the distance between the flame and two electrodes are equal, then the flame will not be perturbed, even you have electric field. Why?
So what are those lines in the first images?
These are lines? It probably is some kind of a streamline. You put some particle there, you take a picture. That is they're showing.
Was it like seeded?
Yeah, seeded flow. And then this is that you can see that the mobility. So what do you mean by mobility? So let's say that the flame generates two different kinds of ions. One is a H3O plus. What is the molecular weight? 19, right? 19? Correct. So the other one you generate ions, let's say a nitrogen ion, is 18. So almost equal. So the negative ions go that direction, the positive ion go that direction. They cancel. The ionic wind, they cancel. So they don't have this kind of a perturbation, even though you have wind. The wind is flowing, but the flame in the middle is still there. Okay? But what if that you have a closed system, that you have a wall, you build a wall there. The ionic wind still will have to flow. And that if the ionic wind will flow this direction, and you heat the wall to form the recirculation. And this way, the negative ion form a recirculation. So you form this kind of a recirculation. So ionic wind not only can change that flame shape, but also causing internal flow recirculation if that in a closed system, right? And then what if that the mobility of the negative ions and positive ions are different? For example, electrons and H3O plus. One is electron, the other one is helium. Then this ionic wind flow will be unsymmetrical, right? So therefore, you can see that the flame, in this case, they move into this direction because heavy ions move into that, and then the little electrons move to this. Electrons is very light. If a heavy ion move, electron, what will electron will do? Electron, they cannot move to that direction because it is attracted by the heavy ions. They will follow you, right? So the heavy ions win, right? Ionic wind, not electron wind, right? So therefore, if you have heavy ions on this way, and then the wind will go this direction. And if you change the electrode, they will go that direction too. So this is the very basics of the dynamics of ionic wind, right? Very simple. But why people, a very simple thing, why people put a lot of research there? Because the dynamics of flames. Question?
Does it draw any current?
Yes, of course. It draws current. You have to have a power to put it. If you have no power, and the ion will not flow, right? So otherwise, you have to have a energy to work to make the ion to move. Okay, go ahead.
I think it looks like image C of the candle flame.
This one?
Yeah, that one.
Yeah.
Is that a microgravity one, or how do you get a flame to look like that?
I don't know whether it's a microgravity or not, but I think that I don't know. You have to look at this paper here. It might be yeah, that looks like a very half sphere. Looks like that the gravity is not playing much role. But the microgravity is more spherical, unlike that. Probably somewhere between, depending on the scale of the flames, right? If the scale of the flame is really small, and the buoyancy does not play too much role, right? So ionic wind. So basically that you have electrical field, and you have a charge here, and this charge and electric field generate a force. And this is basically, and you'll be using non-dimensional analysis, you can estimate that the magnitude of ionic wind is proportional to the charge density, which is here, and Coulomb per cubic meters, and multiplied by voltage and divided by the density of the flow. So if you looking at this, let's say you have oxygen negative, you have a H3O plus, the mobility of the molecular weight is almost similar. And you can see that the negative ions go into this direction, and the positive ion go to that direction. They pretty much cancel each other, equal mobility, right? On the other hand, if you have electrons, then the electrons attracted by the ions, and most of the ions go this direction, and the electron velocity is very small because they are attracted by the ions, right? So therefore, in summary, you can see in flames, most of the ions are positive ions, H3O plus, for example. Electron mobility is high and small mass, and then its motion is reduced by the motion of positive ions. So electron motion does not create much about that any wind, but electron motion contributed to the heating, because electron easily absorb energy from electric field, right? mv square. The V is large, it's V square effect. And therefore, ionic wind is by negative ions, and electrons is sometimes is mostly smaller by positive ions in flames, okay, in flames. So here is a beautiful picture by Professor Cha. Right now he's in KAUST. And any of his students here? No, no one is here. Okay, so he did this experiment. You can see that he put probably a flame a premix flame or a diffusion flame, and put the electric field in that direction. And this electric field can be a negative to positive, symmetrical. You can see that you put the negative, the flame towards this direction. You put a positive, the flame go to that direction. It's all because that is the evidence that in this flames is caused by positive ions, right? Because they switch the direction and fall into. And this is a diffusion flame. You have more soot. The soot is almost easy to get charged by the charge. So you can see that with the same, we can see more dynamic effect, and in terms of diffusion flame. So this is ionic wind, right? So how can we affect it? Why is that people are interested? Because of the dynamics. Here is again is Professor Charles, and a beautiful and recent picture. You can see you have a Bunsen flame, and you can see from the horizontal, you can see from the top, and this is at 0 kilovolt. Electrode is here, and another ground electrode here. So let's put a negative charge. Negative charge means the positive ion will move to this direction. So therefore, that you can have a flow. You can see that from the top, the flame is bended towards this negative electrode, and bended more if you have higher. And then this causing some kind of a flow. Not only the flow moving towards this direction, but also some kind of negative ion flow to this one. A flame is not just positive ions. You have both, positive and negative, right? Negative will move to the positive electrode, and positive ions will move to the negative. You have this kind of a flow. So you can see the flow is going to this one for negative ion, and positive ion going that one in that direction. You're causing this kind of induced circulative flow in a confined environment, correct? Okay, so if you move to counterflow flame, that's what he did the experiment. You can see that if you have electric field going this direction, and you form a flame between, it could be a non-premix flame. So let's say that it's 0 kilovolt, you have a flame in the middle, you have anode, but there's no voltage anyway, so you have flow. This is stagnation flame. But if you put a voltage, let's say half kilovolt, a 1.6 kilovolt, and what do you see from here? You can see here that the stagnation flame changed. And then you have 2 stagnation flame here. So I saw the time is there, so I take a break, and then we look at the before picture. Thank you.